Welcome to our paper, A Type and Effect System for Object Initialization. I'm Fengyun. This is joint work with Ondřej Lhoták, Aggelos Biboudis, Paolo Giarrusso, and Martin Odersky. Object initialization is a 50-year-old problem since the introduction of object-oriented programming in the 60s. The problem can be demonstrated by this simple program. In this program, the user intends to print hello world, but instead he gets hello null at runtime. The cause of the problem is that the field name is used before it is initialized. Accessing a field before its initialization is the source of all initialization errors. Unfortunately, 50 years after the introduction of object-oriented programming, mainstream programming languages such as C++, Java, Scala, C#, etc. are still suffering from initialization errors. Joe Duffy, a former compiler engineer at Microsoft, in one of his blog posts wrote, quote, "Not only are partially constructed objects a source of consternation for everyday programmers, they are also a challenge for language designers wanting to provide guarantees around invariance, immutability, concurrency safety, and non-ability." Initialization problems also exist in functional programming. In functional programming, there is the famous construct for creating mutually recursive bindings, network. Mutually recursive bindings also suffer from initialization errors, as this piece of OOPSLA code demonstrates. We have seen that safe initialization is a common problem in programming. But what makes the problem challenging? A naive solution to the problem of object initialization is to simply disallow the usage of this before the underlying object is initialized. However, there are at least two valid usages of this inside the constructor. The first requirement is to call methods and access already initialized fields on this. The need to call methods on this is confirmed by an empirical study which reports that over 80% of constructors include method calls on this. The second requirement is to alias this to create cyclic data structures, as this program demonstrates. There are several challenges that make it difficult to safely support the two requirements in an initialization system. The first challenge is about virtual method calls, because we generally do not know the targets of virtual method calls at compile time. This program, when run, will result in null pointer exception. The cause is that, according to the semantics of Scala, the soup constructor is executed before that of the base class. Therefore, the field extension is initialized with the virtual method call this.name. The implementation of the method name in the subclass, however, accesses the field local file, which is not yet initialized. The second challenge is related to aliasing. It is well known that aliasing complicates reasoning about programs. Reasoning about initialization is no exception. For example, in this piece of code, the field A is an alias of this. Despite the fact that the field A is initialized, we have to use it with care. For example, the code A.C should be rejected because it accesses the uninitialized field C. There are more challenges to develop an initialization system for a real-world language, such as trees, first-class functions, inner classes, and properties. A practical initialization system should be able to handle all these language features. Reasoning about initialization is critical in the design of initialization systems. We uphold local reasoning in the design of initialization systems. Roughly speaking, local reasoning means that in an initialized environment, we may only produce initialized objects. For example, suppose the environment variables x and y both point to initialized objects. Then local reasoning enables us to conclude that the result of the expression new cxy is an initialized object. The same goes for the method called x.my, no matter whether the method m is a virtual method or not. Local reasoning about initialization is very natural. It's close to how programs reason about initialization in daily programming. Meanwhile, it avoids the need for whole program analysis, therefore gives rise to faster algorithms for safe initialization. One contribution of our work is to provide a modular understanding of local reasoning as the result of three simple properties, namely weak monotonicity, stackability, and scopability. Weak monotonicity says that initialized fields continue to be initialized. Therefore, assigning null to an initialized field should be disallowed. Stackability says that all fields of a class should be initialized at the end of the class constructor. If we draw the initialization period of objects, we would find that the initialization periods of objects are properly nested if the language follows stackability. Scopability says that there should be no set channels for accessing uninitialized objects. Global variables and their control flow effects such as algebraic effects may serve as set channels for teleporting values and initialization. Therefore, in languages that have those features, the initialization system should check that only initialized objects may be teleported. Based on the insight of local reasoning, now we're going to develop a type-based model for safe initialization. A type system depends on abstractions. We propose three abstractions for initialization, namely code, OOM, and heart. A code object may have uninitialized fields. A OOM object has all its fields initialized, but it may reach code objects. A heart object is transitively initialized, or equivalently, it only reaches OOM objects. If we lift the abstractions code, OOM, and heart to types, we arrive at a type system for safe initialization. Here is how the type system works. The expression new child this retains an OOM object because all fields of the object are initialized thanks to stackability. The object is not hard at this point because it reaches this, which is yet code. As the system knows that the field child is OOM, the expression child.name at line 3 is legal. In contrast, at line 8, accessing the field child on parent is illegal because the field parent is code at this point. We have seen that weak monotonicity is sufficient for local reasoning. However, for initialization safety, we need stronger concepts of monotonicity. Past research has identified strong monotonicity as a good design principle. Strong monotonicity says that a hard or OOM object continues to be hard or OOM. With strong monotonicity, this program will be rejected because the initialization state of the object pointed by A is hard. For it continuing to be hard, we may not assign a code object to its field. Our system emphasizes an even stronger notion of monotonicity, namely perfect monotonicity. Perfect monotonicity in addition guarantees that the initialization state of fields is monotone. That is, if a field is hard or OOM, then it continues to be hard or OOM. With perfect monotonicity, this program will be rejected because the initialization state of the field B goes backward. Perfect monotonicity makes it much easier to safely use already initialized fields in the constructor. The type-based model gives us a sound initialization system. Next, we're going to develop an inference system for the model. First, why the type-based approach is not great? There are at least 4 drawbacks of the type-based approach. First, it incurs syntactic overhead, which harms usability. Second, it is inadequate to handle complex language features like trees, inner classes, and properties. Third, it doesn't handle inheritance well. And finally, they require changes to the type system, which makes integration with compilers more complex. A natural idea is to perform inference for the type system. Here, we use a standard analysis technique called type and effect systems. In type and effect systems, each expression is associated with both a type and its effects. The effects can be latent in a function, and they accumulate in function applications. Java checked exceptions is one example application of type and effect analysis. We may easily specialize the effect domain for object initialization. In this piece of code, the expression this.y accesses the field y. Thus, we are associated with the field access effect this.y bound. This effect is illegal at this point because the field y is not yet initialized. This example demonstrates method call effects. The expression calls the method m, therefore we are associated with the method call effect this.mDiamond, which is a proxy to the actual effects in the method. This.m is rejected because it leads to the field access effect this.b bound, but the field b is not yet initialized. One challenge is how to deal with aliasing. Our contribution here is to introduce the concept of potentials to control aliasing in a type and effect system. We illustrate the idea with this code example. Here, the field A is an alias of this. Thus, we associate it with the potential this. The expression this.a has the potential this.a, which is a proxy to the actual potential of A, which is this. The expression has the effects this.a bound because the field A is accessed. Therefore, if we continue to select the field B on this.a, the system knows that the uninitialized field B is accessed. It thus reports an error. This example demonstrates how to use potentials to control escape of uninitialized objects. Here, the field A is an alias of this, thus it has the potential this, and the expression this.a has the potential this.a, and it has the effects this.a bound. In the function call f this.a, the function requires that the arguments to be initialized to conform to the requirement. The system produces the promotion effect this.a up arrow, which means that the potential this.a should be hot at this point. The code will be rejected because this.a is just an alias of this, but this is not yet hot at this point. Note that promotion is the same as requiring a value to be hot. To summarize, potentials represent potential aliasing of objects which are potentially under initialization. There are 3 fundamental potentials, this, on, and code. A potential can be refined by field selection and method calls. Effects represent operations on objects potentially under initialization. Effects can be field access, method calls, or promotions. The high-level idea of the inference system is that each expression is associated with a set of effects phi and a set of potentials pi. If the set of potentials pi is empty, then the value of the expression at runtime must be hot or initialized. How does the solution work in practice? We implemented an initialization checker in the Scala 3 compiler. The checker is implemented as a compiler phase it requires zero changes to the core type system. To help programs easily diagnose initialization problems, the checker shows stack trace that leads to an initialization error. We run the checker on about 500,000 lines of Scala code. It achieves about 0.6 warnings per 1,000 lines of code. To summarize, our work provides a modular understanding of local reasoning. It proposes the abstractions of cold, warm, and hot. We propose an inference system for initialization, which demonstrates how to control aliasing in type and effect systems with the concept of potentials. We implement an initialization checker in the Scala 3 compiler and evaluate it on several real-world Scala projects. For more information, please check out our OOPSLA paper.